So our next speaker is getting set up. So we're going to hear from Rodolfo Canto Torres, a joint work with Nicolas Sendrier. And the topic of this work is analysis of information set decoding. Well, we've heard a little bit of that, but this time it's for sublinear error rate. Welcome.
Good morning, everyone. Today I want to present good morning, everyone. Today I want to present a theoretical result done by Nicolas Sendrier and myself. This theoretical result was motivated by Sendrier estimation about complexity of decoding algorithm. I begin by introduce basic notion about my article, our article, and describe fast the principal result. After I will talk about more about the algorithms which we studied. After, we describe more or less how they work. I will make some estimation about their complexity. With this estimation, I will start the synthetic analysis for case, and after for the last algorithm in this branch. The algorithm of May and Azeroth proposed the last year. Finally, I will show some estimation about the synthetic complexity, non-asymptotic study about this complexity. Well, I begin by recalling the computational syndrome decoding, CSD, and this is the length of the code, K the dimension, and W the weight of the error which we want to correct it. We have a parity matrix H, and syndrome S, and weight W. We must find E such that he has a smaller weight than W and the syndrome S. This problem is believed to be hard on average. As we can see between this conference, this problem is central for the security of code-based cryptography. The first important algorithm, the information set decoding, was proposed by Branch in 1962, and the last one by May and Azeroth in 2016. By ISD, I will always understand in information set decoding. Yeah. It's normal to analyze the complexity of this algorithm in terms of the decoding rate R, the error rate tau, which tau is smaller than the Gilbert-Bachamot bound. Here, H is the entropy binary function. So, for an algorithm, we can express usually as this is exponential expression in function of n, C prime will be a constant, which depends of the coding rate, the error rate, and the algorithm we study. Well, in our work, we focus on the case where W is sublinear to n. For this case, we change the scale of our exponential expression. I mean, I will express the complexity, the word factor, in function of W. Here I remark that this little o of 1 means that I will omit some polynomial term. Yeah. Our objective is to show for many variants of information set decoding and coding rate constant when the weight is sublinear to respect n, then the word factor is expressed like that, and the constancy becomes the same for all the variant we will study. Here we can see the five how the five algorithm we will study is developed. How the coefficient C goes when we increase the error rate. We can see from the algorithm of branch and Ocerot, they are very different when they are near to the Gilbert-Chaumont bound, but they becomes the same near to 0. After we will show that there is a cause that the error rate is smaller than the constancy. The constancy becomes the same, near to be the same. Yeah. Well, for information set decoding, I mean this was proposed by Pranch in 1962, and I denoted by Pranch ASD. The same for the algorithm of Esther in 1928 and Dummer in 1991. This smaller Dummer is a little better than Esther and very similar. So I put them in the same as the same algorithm, well, as the same variant. After the algorithm proposed by May, Murer, and Thomas in 2011, BJM proposed by Becker, Ju, May, and Murer in 2012, and the nearest and the newest one, the nearest neighbor, proposed by May Azeroth the last year. Well, for information set decoding, I mean, we always, it's possible to obtain a permutation and Gaussian elimination that give me this expression, this form for our problem, where all the error will be in this simple part, and so in this case we only need to verify if this new syndrome has a weight W. So we obtain the error easily. For the other variants, Esther and Dummer, MMT and BGM, we have this framework which make a partial Gaussian elimination and devise the algorithm for solve a subproblem with H prime, S prime, E prime, as which weight will be P. That is a subproblem. Here P and L are parameters to optimize. For this algorithm became branch when the parameter P and L becomes 0. Well, our first proposition talk about how many. Yeah. Well, here I describe shortly how this algorithm work. First, we chose a random permutation, and we devise our system in this new, like the previous framework. We find a list of subproblems, which a list of partial solution to the subproblem. This list of partial solution we will test for to know if it will become a solution, a complete solution. Each algorithm has its own way to calculate its list E that we will change for each algorithm. Well, the proposition. We will run this algorithm, and we can see that the instruction 1 is repeated this number of times. And the instruction 2 is repeated unless this number of times. The second one has has relation with the first in a proportion of the size of the seg E we can see here. So we know how many times the instruction 1 is repeated, the instruction 2 also. So we must to know we must to know how is the cost of instruction 1. Well, for that we look for a lower bound for the instruction 1. So we see what the algorithm does. For Sterman-Dummer, this algorithm produces two lists of size of this size. MMT produce 4 lists of this size. BEM, BJM produce a less produce with list of size unless this one. So because we are interested in the lower bound, we only take the cost. We obtain a lower bound for the cost of the instruction 1, like that. The instruction 1 for MMT, like that. The same for BJM. Well, our proposition, the first one is the work factor of these 3 algorithms are bounded by this expression, which I obtained by the last number, and well, that is always true. This inequality with the branch algorithm for normal parameter. So the idea of the proof is to show this lower bound becomes becomes equal to the upper bound for when n becomes bigger and bigger. large. Well, the main tool for this for to do that is study the function we will minimize. This is the function b sub a in function in L and P. For this, we can recognize the number we see. Yeah. First result we can show easily is to a polynomial factor, we can obtain an equality between the work factor of branch algorithm and the value of the function in 0, 0. So for an special value of the lower bound function, this becomes equal to the upper bound. So we will study what happened with for the optimal parameter. There could be many optimal parameters, but we can show that unless there is a pair of parameters which satisfies this equation. This is an equation in exponential in L and an expression in a combinatorial number. We will find an expression similar to the case of a nearest neighbor. With this expression, with this equation, and our asymptotic hypothesis, we can show that the parameter L becomes also negligible to respect n. So, under this the asymptotic hypothesis, for some pairs of optimal parameter, L becomes negligible to respect n. So we can try to omit this parameter L from the analysis. Therefore, we study this simplified function. For the lower of this function, this is for the lower of the optimization, this function is convex, and his optimal parameter satisfies that this is negligible to this is little o of W. This is negligible to respect a W. So an informal reasoning about that told us that when n becomes large, when we try to analyze this optimal value, is approximately the same that make L and P decrease L and P in proportion to n and W, and thus implies that the parameter P and L will become negligible. So the lower bound will become the lower bound will become the upper bound. More exactly, we obtain this theorem. We have an exponential formula, so we will take a logarithm of this function b sub a, and that will be c sub a, and we will take the limit when n tends to the infinity, and we can show the result. So this limit independent of the parameter a. So it depends. So that is independent of the algorithm. So for all the algorithm which I mentioned, this is the same. Well, I will only give an idea of estimation for the last case, for the case of the nearest neighbor. Well, it's similar to the BJMM, but well, as the conventional information set decoding, we must to repeat the main log this number of times to obtain a good distribution of the error in the word of the weight in the word in the error. This algorithm produces the eight initial lists of BEM, and this also has the same. This also has at least this size. For enough n and k, we have this inequation, this inequality, this expression of minimization is subject to this equality. And as I mentioned it before, this kind of expression exponential in function of L, and with binomial term in P, let me conclude that L becomes also negligible to N. Yeah, the parameter epsilon 1 is one of the other parameters of this algorithm. Yeah, this becomes unless it does become big O of P. That we become from that we deduce from this inequality. So we can obtain this inequality where this is the function little b with this number. So we can reproduce the same analysis. Here in this figure, we have the behavior of the constant C for these different algorithms. We see how this how the value tends to 1 for this code rate. Tau is always between 0 and the Gilbert-Bachamot bound. Here is for the code rate 0.65. Another one. Yeah. In the next table, we will see how this that is possible that one code take this parameter, take this error rate as parameter. Yeah. For the quasi-cyclic MDPC code, the weight of the error is a big O of square root of n, and we can see how the security bits, the number of operation we need to do for decoding is not is near to the same. Here I take a log in base 2. This is 2 at 87. As is the same with another value. This is with a low error rate. When the error rate becomes near to the Gilbert-Bachamot bound, we have a little distance between the exponent we have. For the case of the code of the GOPA code, we can see that there is not too similar. Even when the low error rate is even when the error rate is small, and when the error rate is near to the Gilbert-Bachamot, we can see that they are really different. Well, in conclusion, in this work, we introduce a productive way to express the work factor in function in function of the number of error. We can see that when the weight is smaller, is negligible to m, with respect to m. We can obtain one approximation, one value near to the real value. This result allows us to explain the behavior of the decoding algorithm for the case of the quasi-cyclic MDPC code. And thus, this kind of resistance to the generic decoding is a good reason to propose quasi-cyclic MDPC code as partner for mechanical crypto system. Thank you for your attention.
Okay, thanks for the presentations. Are there questions? Dan up there.
Can you comment in more detail on how this relates to the work in Christiane Peter's thesis? Obviously, that was before some of the most recent algorithms, but the basic shape of the 1 minus r and so on seems very similar.
I don't know which more exactly was which word.
It's the PhD thesis of Christiane Peters from some years ago. The title is Curves, Codes, and Cryptography. It's online.
Do you mean the algorithm of the ball decoding?
That's also in the thesis, yes, but there's the analysis paper included there on the asymptotics of decoding algorithms, ISD-type decoding algorithms, several different algorithms of that type, what they look like for decoding when there's a sublinear number of errors. So I was wondering if you could compare in detail to what's happening there.
I didn't read it.
Okay, thanks.
Okay, I'm having a side conversation with a co-author who says he wasn't aware of it. Okay, so there's something to take up afterwards. Any more questions? All right, I get this feeling that announcing that the coffee break would be longer is counterproductive for questions. Going once, going twice. All right, so we now have a coffee break till 11:30. Please be back for the invited talk afterwards. And please join me in thanking the speaker again.